This video explores a mathematical discovery about the nature of prime numbers, often called the law of the primes. It shows how a 15-year-old boy, Carl Friedrich Gauss, first saw order in the chaos of numbers. Prime numbers are the indivisible atoms of arithmetic, whole numbers greater than 1 with exactly two factors, 1 and themselves. They are the building blocks from which all other numbers are made. This is known as the fundamental theorem of arithmetic. The question of whether primes end was answered around 300 BC by Euclid, who proved they are infinite. His method shows that no matter how long a list of primes is, you can always generate a new number that proves the list is incomplete. The Sieve of Eratosthenes is an elegant algorithm for finding primes. By circling a prime and crossing out its multiples, we can filter the integers. This process not only gives us a list but also provides data to study the frequency of primes as numbers grow. Counting primes in blocks of 1,000 shows a clear trend. Their density is dwindling. While Euclid proved they are infinite, their frequency decreases. This was the key clue that captivated the 15-year-old Gauss. Instead of density, we can examine the average gap between primes. This is calculated as x divided by pi of x, where pi of x is the number of primes up to x. The resulting curve shows the average gap growing steadily, suggesting a familiar mathematical function. An unexpected clue comes from compound interest. As interest compounds more frequently, the final amount approaches Euler's number, E, the base of natural growth. This is roughly 2.718. The inverse question, how long did it take to reach a certain amount, is answered by the natural logarithm ln of x. The shape of this logarithmic curve, which starts fast and rises more slowly, is the one we were looking for. Comparing the actual average prime spacing with the natural logarithm reveals a striking similarity. This relationship is the prime number theorem. It states that as x gets larger, the number of primes up to x is approximated by x divided by ln of x. The law was refined by Legendre in 1808 and by Gauss, who recalled his findings from 1792. Gauss argued that the true density is 1 divided by ln of t, and proposed the logarithmic integral, Li of x, for a more fundamentally correct total count. Gauss's insight was deeper. While Legendre's formula was accurate for smaller numbers, Gauss's LAIX prediction, when compared to the actual prime count, showed that his method becomes more accurate over the long term. Legendre's fixed constant was a flaw. In 1859, Bernhard Riemann reframed the problem using the Riemann zeta function. The final proof of the prime number theorem was achieved independently in 1896 by Jacques Hadamard and Charles de la Vallée-Poussin, establishing Gauss's law as truth. Progress often begins with data. Gauss counted, letting the numbers guide his intuition. As he said, "It is not knowledge, but the act of learning, not possession, but the act of getting there, which grants the greatest enjoyment."